is a new age of physics and the understanding of our universe. We've never before seen these unprecedented energies that the collisions will be at the Large Hadron Collider. Whatever is out there, we're bound to see it and we're bound to discover more and essentially rewrite the textbooks.
These kind of detectors and experiments come about once in a generation, and it is a great privilege to have been part of this from the start.
This looks like a lovely crystal, but it's actually really heavy. I can only just lift it. This is part of the electromagnetic calorimeter, so particles get detected here. They produce light in the crystal that is then detected by this piece of electronics here.
One of the possible things that we'll see at the LHC are signs of a new particle called the Higgs particle. Now, if this exists, it could explain why some other particles are heavy and some of them are light. This detector in particular will really give us a handle on whether this Higgs particle exists or not.
I'll be very, very surprised if something isn't found soon.
Thank you, Mr. Ellis.
This is a very unusual place to be. Most of the visitors who come to look at Atlas don't actually get allowed to come right in the heart of the experiment, which is where we are now. We're just underneath where the beams of protons from the Large Hadron Collider are going to collide. Atlas is the largest of the 4 experiments that are being assembled around the Large Hadron Collider. What we're really hoping is that Atlas is going to give us some clue into also the mysteries of astronomy. We know if we look out at the cosmos, there's a certain amount of visible light from stars and so on, but the way they're moving, astronomers and cosmologists know that there's actually more matter out there. There's some dark matter out there which has so far not been observed, something really new. We're hoping that in Atlas we will actually be able to create particles of dark matter.
On the cosmological scale, we're reproducing here by colliding 2 protons at these energies, events which happened right at, we believe, at the Big Bang.
The sheer amount of power we need means that we start with the very highest voltage, 400 kilovolts from the French network here. If we're going to find new particles, we have to put a lot of energy in to create a small amount of mass. And the sheer amount of the hundreds of megawatts that we draw from here to produce these very smallest particles is very impressive.
The LHC is a voyage into the unknown. It's tremendously exciting because we really don't know what we're going to see there. I literally can't wait for everything to start up to see what we're going to find in the data. The green curves you can see here belong to the magnet inside the LHCb experiment. What happens when we have a beam collision is we create lots and lots of fundamental particles, very energetic ones. They rush out in all directions, and the job of this magnet is to deflect them, and that allows us to work out how fast these particles are going. We've never looked so deeply into the heart of matter before.
Finding extra dimensions would be much more exciting than finding a ball-ring Higgs boson, possibly even more exciting than finding dark matter. This would be telling us something really basic about the way in which the universe is constructed, something completely unexpected if it's true.
My group are involved in the ALICE detector, and what's unique about ALICE is that as well as colliding protons together, we take lead atoms, we strip off all the electrons, put them in the LHC, collide them to the maximum energy. We create an incredibly intense fireball. Now there's nothing to be afraid about because this fireball is much, much smaller than the size of an atom, but it's incredibly hot and incredibly dense. In fact, it's about 1,000,000 times hotter than the centre of the sun. And it's so dense, it's a bit like taking one of the great pyramids of Egypt and crushing them to the size of a pinhead.
This is really the biggest and most complex scientific project ever undertaken. The whole 27-kilometer circumference is aligned to better than a tenth of a millimeter. The way that we cool the machine down is very unusual. We are using superfluid helium, which is a very, very odd liquid. It's a quantum liquid. For instance, if you put it in a beaker on your table, then the liquid would just crawl out of the beaker.
I'm working on minimum bias trigger and trigger for first physics, and actually looking at how the trigger biases the events that we collect.
I'm looking at the phi meson, which is a particle that will be produced in the collisions, and it's made of a strange quark and an anti-strange quark. And these are really interesting because things that have strange quarks in could be a signature of a quark-gluon plasma.
Everybody from all over the world is going to come to Europe, and that's going to be the center of all the activity, and I'm right in it.
People have a lot of stereotypes about people doing physics, that they should be all male and that they should be wearing cardigans with patches on and glasses with tape around the middle. And no, we're not like that at all. So. Well, some are, I suppose. But.
For me, as a theoretical physicist from Cambridge, I've got to look at the results after they've come out and actually after they've been published. Theoretical physicists think in a peculiar way. We have on the coffee tables, we have glass and pens there, and there are blackboards everywhere. It's very annoying not to be able to write something down if you need to. I'm sure I dream about the mathematics in my sleep, and I've solved problems in my sleep. CERN is a hot pot of all the best brains around that are interested in particle physics. It's the temple of physics, and all the top acolytes go there.
The LHC is a compulsory tool. Without the LHC being built, we will know that a big part of the knowledge is missing, and we'll have no way to discover it.